We discussed how we can implement a MergeSort algorithm in Java. Let's now talk about the running times for the algorithm, for the implementation, which is recursive. So there are two ways for us to carry on with the discussion. One would be to look at the recursion tree and try to figure out visually exactly what a running time would be. Basically, we want to analyze about what a running time would be at each level of the recursion tree, and then talk about how many levels do we have in total, and then multiply these two numbers together. That would be how I would start with analyzing the running time. And the second way to do it would be similar to how we analyzed the binary search running time earlier in the recursion lecture. We have to first of all derive the recurrence relation based on the Java code, and then we have to solve the recurrence relation. So there are two approaches. Let's do one by one. The first one, as you can see from the slides over here, this is basically the abstract version for the recursion tree for the MergeSort. So you can think about, we start with the list of size n. So this will be the entire list. And we have to somehow keep splitting it until we reach the bottom level over here of the recursion tree, where every list that's unsorted is of size 1. Basically, that's what we have to do. And then we have to go back and merge each of the unsorted lists one by one. And we want to think about what the running time would be whenever we want to do some merge. Let's now, first of all, go back to the merge method that we have to call for every recursion. Let's talk about it, and then we'll go back to this diagram here and to see what the running time should be overall. Right, so if you go back to your earlier notes, you can see this is the implementation for the merge over here. And this was the little example that we went over earlier. You can definitely refer to the earlier lecture, earlier part of the lecture. And let me go directly to analyzing the running time over here. You can see we try to assign I and j counters over here. And then the first while loop, think about when it is supposed to terminate. We're saying that it will actually keep looping as long as I should be strictly less than the size of the left list, and j must be strictly less than the size of the right list. And how many iterations are we going to run from this while loop? That's something we can figure out right away. Whichever shorter list it is going to be exhausted first, and then that'll be the time to terminate the loop. So it will be the minimum size of the left and right. It will be very important for you to note that over here. The number of iterations over here is going to be the minimum of the size of the two lists. You can think about it's so we got L and we got R. So L dot size and also R dot size. This is the first detail you have to make sure you understand about how many iterations there will be. Right? Let me use a different color here. How about just yellow? That should be okay. Right? That's about the number of iterations for the first while loop. What about the next two for loops? They are not really nested, so they should be about just linear, but we want to understand a little bit further. So we the logic would be whichever the minimum of the list is. For example, let's say if the left list is the one with the shorter length. In that case, the left list is going to be exhausted first from this particular loop. In that case, we haven't really exhausted the size of the larger length, which is the right in this case. In that case, we still actually have to go over the remaining part for the right list and complete it, right? So you should really understand the logic for the method. And let me just highlight to you over here. Okay, so this part over here, the number of iterations is going to be as follows. Okay, let me just put down in words over here, and then we try to add up the two numbers together. So the number of iterations will be the remaining number of items to loop over in the longer list, because the shorter list has been exhausted already. In the longer list, because we know that the earlier loop is going to exhaust the shorter list first. So that means the longer list still has some remaining items to be looped over, right? And let's think about what's going to happen if you try to add up these two numbers over here. You can think about this is the first number over here. Let me call this maybe just A. And this one over here is simply just B. What would be A plus B? A plus B. Well, you can pause the video and think about what the sum would be, right? Hopefully you thought about it. The sum should be, obviously, let's say, for example, if this is the left and this is the right, let me draw that just strictly smaller, just for illustration. The first while loop over here is going to exhaust the shorter list first. And at the same time, it may have exhausted only up to this part over here for the longer list. That means we still got this remaining part, which is going to be exhausted by the first loop in this case. Of course, the case will be symmetric if it turns out the right list is actually longer. I'll let you do that illustration yourself. Right? But we're still going to exhaust this. So overall, we're really exhausting all the elements to loop over in the left list, and also all the elements in the right list to be exhausted as well. So overall, the number of iterations after the while loop and the two for loops will be simply equal to the length sum of the two lists. Right? That's very important for you to conclude as well. So that will be simply just left dot size plus right dot size. This will be very important for you to actually know, right? So this will be the running time over here. So that'll be the big O you actually see on the slides for the merge method specifically. Now that we understand this, we can now return back to the recursion diagram over here, right? So let's now go back to the recursion tree over here. So we start with, for example, we start with the N over here. That's the entire unsorted list to be sorted to begin with. That's the overall input. Let's say after the first split, we split it into the left list and the right list, and normally they should be around equal length, but sometimes it could be maybe one element more than the other. But the point is, if the length of the left is actually n over 2, the length of the right is n over 2 as well. In that case, we know that the merge routine to really merge these two lists will actually take big O of n. And by the way, why would that be big O of n? If you look back to the actual body of the loop, they are all to do with, you can see relational expression over here, and also some method to add to the end of the list. In that case, it will also be constant, and also to get index from the list, which will be also big O of 1. So you can assume that all the operations inside the loop body over here, they would just be big O of 1. That's also something worth noting. Big O of 1 over here, and also for the body over here, that's also big O of 1. That's also big O of 1. So that's why when you actually talk about the running time, it's going to be the number of iterations, which will be the summation of the sizes multiplied by 1. Right? So that'll be the big O of L dot size plus R dot size. That's for individual merge method. But if you go back to this bigger picture about a recursion tree, if I want to merge a list of size n over 2, another list of size n over 2, so that should be big O of n. Exactly, right? The size summation. And similarly, if I go to the next level, because I know that this list is going to be also split into n over 4, n over 4. That one there is also split into n over 4, n over 4. What will be the running time? For example, what will be the running time to really merge these two lists, right? That one should be merged first. This one should be big O of n over 4 plus n over 4, which is big O of n over 2. And also for this one over here, it's going to be similar, right? That one is going to be also big O of n over 2. And if you try to add them up together, it's going to be big O of n. Right? Of course, you can also try to say it's the big O of n over 4 plus n over 4 plus n over 4 plus n over 4. That'll be big O of n as well. That's another way to derive it. Right? So the big O of n is going to be true for every level of the recursion. Let's verify this in the example that we went over before. If you look at this tree over here, recursion tree, when we get to the bottom level over here, the first merge that we have to do, think about the merge that we have to do. let me just say, just look at the purple, okay? I just want to annotate on top of what we went over already. So this part over here is going to be one merge over here, and this part over here is going to be another merge at the same level. This will be another merge over here, and this will be another merge. If you try to count, for this particular merge, the sum of the length of the two lists will be 1 and 2. 1 and 2. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. So the running time will be actually 8. If you think about it, it will be 8, which correspond to the original size of the list. 1, 2, 3, 4, 5, 6, 7, 8. Similarly, if you go to the level up, we try to merge these two lists over here, and also we try to merge these two lists over here, even though the number of merges will be reduced. However, the size for the left and right have been increased. So if you think about the running time, it's going to be 1, 2, 3, 4, 5, 6, 7, 8. So you still have 8, right? So it's going to be true for every level. Big O of n, and also big O of n. It's going to be true for every level, right? Hopefully now you got enough stuff for you to understand why for every level, for the merge, the running time is going to be big O of n. To really know the overall running time, we want to know how many merges should we do. It depends on how height the tree is, right? So to really know the tree of the height, this one really corresponds to the height of a balanced binary search tree. Okay, over here, this will be really correspond to the heights of a balanced binary search tree, right? Which is the minimum possible heights for a binary tree where the number of nodes is actually n. This is kind of related to your lecture about balanced binary search tree lecture. You can definitely look at that. Also, when we talk about the general tree and binary tree lecture, we also try to work out the bounds for the number of nodes and also the height number for binary tree. So this part here, I'm going to assume you actually know. Because the way we actually got a recursion tree branch out is actually very regular, right? Always we branch out by just by 2 and by 2. So the entire tree over here is guaranteed to be a full binary tree. Okay. Another thing I want to just mention quickly. So the recursion tree is a full binary tree. That's also very important for you to actually realize. Alrighty, and what will be the total running time? The total running time, I'm going to write it down over here. The total running time is going to be, how many levels do we have? Big O of the number of level is really log n, because it's a full binary tree that's balanced. Multiply by, at each level, we're going to do the merge that will boil down into just merging n elements. In that case, it's going to be multiplied by n. And that's simply equal to big O of n log n. Right? So that's the final answer for the running time. Right? Quite a bit of discussion over here, but I think it's really important for you to link from how we trace the recursion and how we did a merge over here and then work out the total running time based on the recursion tree diagram over here. That's the first approach I would like to speak about. And the next part will be to talk about how we can derive the running time based on the recurrence relation that we can derive from the Java code. And we'll talk about it in the next part.